Hey people, let's start learning for earning.
Look at this industrial steel rolling mill. The electric motors driving these operations face immense mechanical resistance, requiring continuous power at the megawatt scale. To control the speed of these heavy machines, operators cannot simply reduce the voltage. They must precisely alter the frequency of the alternating current supplying the motor. The standard method for changing frequency is a multi-step process. Convert the grid's AC power into DC and store it in massive capacitor banks. It's then synthesized back into a new AC frequency. At megawatt power levels, those intermediate capacitors become dangerously large, causing heavy energy losses. Achieving true high power efficiency means cutting out the middleman entirely. Engineers need a way to bypass the intermediate DC link and synthesize the target frequencies directly from the raw incoming AC grid. The solution is a highly specialized power electronics topology called a cycloconverter. A cycloconverter takes alternating current at a fixed input frequency and mechanically switches it to output an adjustable, lower frequency AC wave, entirely eliminating the direct current stage. Outline the roadmap for this lesson, derive anti-parallel SCR switching logic, scale into dual bridge topologies, account for inductive heavy loads, and examine the constant V/F ratio. Mastering this specific circuit gives engineers the ability to efficiently command the most powerful electric traction systems and industrial induction machines in operation today. To build a machine that divides grid frequency, we have to start at the component level, controlling a single AC sine wave using silicon-controlled rectifiers, or SCRs. This diagram shows the foundation of direct AC control, an anti-parallel configuration. Here we have SCR1, which is oriented to handle the positive voltage from the AC supply, while another SCR is positioned to handle the negative voltage. A gate signal allows SCR1 to conduct during the positive half cycle. Because it is connected to an alternating current, it will naturally turn off the moment the current drops to zero. As the voltage polarity reverses for the negative half cycle, SCR2 receives its gate current and begins conducting. Notice the right side of this circuit. This is the auxiliary commutation path. While natural commutation works at the zero crossing, sometimes an SCR needs to be turned off early. The auxiliary circuit contains a capacitor that charges while the load receives voltage. Firing the auxiliary SCR2 releases that stored energy. The capacitor discharges in the opposite direction through SCR1. When this opposing discharge equals the forward current, SCR1 is forced to turn off early. This arrangement operates as a highly precise static AC circuit breaker. It gives engineers the ability to slice specific segments out of an AC waveform, which is the exact logic required to build a frequency converter. To physically divide the frequency of the grid, a single switch isn't enough. We have to scale up to a dual bridge rectifier topology. This schematic shows a single-phase cycloconverter. Notice the symmetrical layout. It uses a positive group of thyristors on the left and a negative group of thyristors on the right, both linked to a central load. The control circuit fires the thyristors in the positive block over the span of several fast input cycles. By controlling their firing angles, this group synthesizes a sustained envelope of positive voltage across the load. Once that positive envelope is complete, the firing pulses shift. The right block takes over, producing a sustained envelope of negative load voltage by driving the current in the opposite direction. There is a strict operational deadband required here. When one converter is operating, the opposing converter must be completely disabled. If both fire simultaneously, it creates a direct, catastrophic short circuit. Cycloconverters operate in two modes. Step-up versions output higher frequencies, but they require complex forced commutation circuits to artificially interrupt the current. We are focusing on the step-down cycloconverter. Because the output frequency is lower than the input, the thyristors can rely entirely on natural commutation, turning off seamlessly as the high-frequency input voltage naturally crosses zero. By logically passing control back and forth between these two bridges, the system physically weaves a brand new, lower-frequency AC wave directly out of the incoming grid power. That dual bridge sequence is mathematically straightforward, but only if the industrial load is purely resistive. In heavy machinery, that is almost never the case. If you look at this graph of a purely resistive load, the current waveform perfectly matches the shape of the output voltage. They rise and fall in unison, naturally commutating at the exact same zero crossing. But an electric motor is a highly inductive load. In an RL circuit, the current waveform significantly lags behind the voltage waveform. This phase shift creates distinct zones where the voltage drops below zero, but the current is still positive. This occurs because the inductor stores energy in its magnetic field. When the SCR attempts to turn off at the voltage zero crossing, the collapsing magnetic field forces the current to continue flowing. This stored inductive energy acts like a temporary generator, feeding back into the system and causing the load voltage polarity to reverse until that lagging current finally decays to absolute zero. To prevent the cycloconverter from shorting itself out under these conditions, the firing circuits must be aggressively reprogrammed. The controller continuously calculates the phase angle and delays the thyristor gating pulses to match the current lag. The physics of inductive energy storage forces a significant delay in commutation, requiring the control system to continuously calculate and compensate for the resulting phase lag. Single-phase cycloconverters prove the switching concept, but a single phase produces pulsating torque. Heavy industrial machines require smooth, continuous power. Look at this array. To drive megawatt-class motors, engineers construct a three-phase cycloconverter by linking three independent three-phase to single-phase cycloconverters together. The main grid lines, L1, L2, and L3, continuously feed raw AC power through transformers directly into these massive parallel banks of up to 36 individual thyristors. A centralized microcontroller monitors the input grid and the motor load, staggering the firing sequences across all three thyristor groups simultaneously to manage the extreme power demands without an intermediate DC stage. The outputs of these three massive converter blocks are then wired directly into standard Y or delta motor configurations. This synchronized array outputs three distinct, heavily filtered voltage phases, precisely separated by 120 electrical degrees. By accurately spacing these synthesized output phases, the network generates the smooth, rotating magnetic fields required for high-torque industrial traction. With the switching topology solved, we reach the ultimate engineering goal, precisely controlling the speed of massive AC induction machines. Look at this torque slip curve. Torque is tied to magnetic flux. Changing frequency without adjusting voltage destroys this profile. Lowering frequency alone causes magnetic flux to spike, severely overheating the iron core. Therefore, the golden rule, the voltage to frequency ratio must remain strictly constant. The cycloconverter handles this automatically. Its digital signal processor rapidly adjusts the internal firing angles of the thyristor bridges, delaying or advancing the pulses. This dynamic shifting alters the RMS voltage output at the exact same moment it synthesizes the new target frequency. Because it controls both variables simultaneously, direct cycloconversion maintains constant torque across variable speeds, ensuring flawless heavy-duty control over megawatt drives. Seeing an industrial electric train or a massive mining drill accelerating smoothly under thousands of tons of load means you're watching these principles in action. Beyond motor drives, this exact same topological framework is used to precisely tuning resonance in megawatt-scale industrial induction heating furnaces. The foundation lies in a simple anti-parallel SCR arrangement, acting as a static breaker. Scaled up, that simple breaker evolves into a dual bridge system capable of direct AC synthesis. To make it work in the real world, engineers had to conquer the continuous conduction phase lag of inductive loads and orchestrate complex firing sequences across massive three-phase arrays. By completely eliminating the intermediate DC link bottleneck, cycloconverters provide the raw electrical efficiency and precise mathematical control that powers the heaviest industries on Earth.
Please like, share, and subscribe for more learning and appreciation. I am Batman.